Let's pivot to some of the other forms of ANOVA. R ANOVA is short for Repeated Measures ANOVA. It is an extension of the paired treatment t-test, but there are now 3 or more related groups. In setting up the data set, rows correspond to subjects or participants in the experiment, and the columns represent the various treatments for each subject. As the name implies, R ANOVA is used when there are multiple treatments on the same set of subjects. We wish to determine if a difference exists on average within each of the treatments. The language for the hypothesis statements will follow the same format as those offered in ANOVA. There are numerous assumptions that must be met when running R ANOVA. The first 2 assumptions are grounded in the study design. First, we need a continuous dependent variable. Second, within subjects factors are categorical with 3 or more levels. The remaining assumptions require some data analysis. First, normality of the dependent variable at each level of the within subjects factor. It should be noted that one way R ANOVA is considered robust to violations of normality. The impact of non-normality can further be reduced if the shapes of the distributions of all the within subject factors are the same. There should be no significant outliers at any level of the within subjects factor. Unusual or far apart from data values compared to other data are considered outliers. Sphericity refers to the equality of the variances of the differences between all combinations of levels of the within subjects factor. Put another way, the correlations between the treatment levels are all the same. This is a rather complex condition to visualize and can best be articulated with a covariance matrix. In most situations, sphericity will be violated. This can increase type 1 error. There are a handful of correction factors, such as greenhouse geyser, Hunfeld, and the lower bound estimate, that when multiplied by the degrees of freedom will correct for non-sphericity. Relatively speaking, the greenhouse geyser estimate is more conservative compared to the Hunfeld estimate. Many technologies offer Macaulay's test for sphericity. There are mixed opinions on the robustness of this test, and it could be best to just adjust for a lack of sphericity, conservatively speaking, without checking for sphericity. Using a repeated measures ANOVA approach reduces the unsystematic variance. It also helps to improve and detect experimental effects. There is also a benefit through the need of fewer samples. We must be cautious of fatigue. After all, we are subjecting the same participant to multiple treatments. This could create unforeseen yet substantial bias. In some situations, when using the ANOVA, some of the unexplained variability or error variance is attributed to some additional variable that is not part of the experiment. Removing the influence of this variable could reduce the error variance and allow a more accurate picture of the true effect of the independent variable. This is the intent behind ANCOVA. ANCOVA is short for Analysis of Covariance. ANCOVA is an extension of the ANOVA test with the addition of a covariate variable. The covariate variable is linearly related to the dependent variable. Adding this into the analysis can increase our ability to detect differences between groups of an independent variable. And ANCOVA is used to determine whether there are any statistically significant differences between 2 or more groups, adjusting for the influence of a covariate variable. The hypothesis statements will mirror what was offered for the ANOVA, but must be adjusted somewhat to account for the influence of the covariate variable. For example, we could use a one-way ANCOVA to determine whether driving ability differed based on the age of the driver while controlling for the driver's GPA. The dependent variable would be the driving ability, measured from 0 to 100. The independent variable would be the age group, which has three groups: 16 to 18, 19 to 21, and 22 to 23. The covariate would be the driver's GPA. For an ANCOVA, we will be controlling for the driver's GPA because we believe that the effect of age on driving ability will depend to some degree on the academic performance of the driver. The table here shows how the data could be organized. There are numerous assumptions that must be met when running ANCOVA. Unlike other parametric tests, ANCOVA does not have a non-parametric equivalent. The first four assumptions are grounded in the study design. First, we must have a continuous dependent variable. Second, the independent variable is categorical with two or more independent groups. Third, the covariate variable is continuous. And finally, independence of observations must be assured. The remaining assumptions require some data analysis. First, normality of the dependent variable for each grouping of the independent variable. It should be noted that one-way ANCOVA is considered robust to violations of normality. Homoscedasticity refers to the constancy of the error variances, or residuals, for each group of the independent variable. The graph on the left is indicative of homoscedasticity. Note the constancy of the error variances, or residuals. The graph on the right is indicative of heteroscedasticity. As you trace from left to right, the error variance is increasing. Homogeneity of variances has already been discussed with ANOVA. We have also discussed outliers with ANOVA as well. Additionally, covariate variables should be linearly related to dependent variables at each levels of the independent variable. To test this assumption, a series of scatter plots with best fit lines between the covariate variable and the dependent variable at each level of the independent variable can be generated and examined. Finally, homogeneity of regression slopes investigates whether there is an interaction between the covariate and the independent variable. For ANCOVA, we desire no interaction. Visually, we are requiring that the slopes of the lines we generated in the previous assumption all be parallel to each other. A variant of the one-way ANOVA procedure to determine the statistical significance of the interaction between the independent variable and the covariate variable is typically used. Introducing the covariate, we hope, will help to explain some of the unexplained variance or error variance in the model. Reducing the magnitude of unknowns delivers a more deterministic model. Identifying and controlling known extraneous variables, or covariates, gives us a greater insight into the effect of predictor variables. Like most analysis of variance-related tests, ANCOVA only establishes that a difference exists, but is not capable of determining which specific groups were significantly different from each other. Let's go back to the ANOVA example and introduce height as a covariate variable. The data set appears as shown here. In keeping with the illustrative intent of these examples, we will assume that the assumptions have been met, but we will be exploring the analysis for two of these assumptions unique to ANCOVA. The results for the ANCOVA are shown here. Notice that the p-value of 0.02663 is still below 0.05, but the strength of our result dropped by 1 order of magnitude. In other words, we are not as confident in our assertion with the ANCOVA as we were with the ANOVA. The presence of the covariate variable has delivered a more deterministic result. We also notice that the homogeneity of regression slopes p-value is very large, at 0.7366. This affirms that the regression slopes are indeed the same. The correlation between the covariate variable and the dependent variable is statistically significant, at 0.599395.